Hey everyone. In this video, we're going to look at simple machines and pulleys in particular and see that we can use these simple machines to kind of cheat forces, get more output force than we put into a system, but we can't cheat energy. We can't get more output work from a system than what we put into that system. So let's briefly talk about these simple machines. These are devices that can change the direction or the magnitude of a force. Some examples of simple machines are levers, pulleys, inclined planes, wedges, gears. There's a number of different kinds of simple machines that have these kind of similar properties. And one of their key properties is that, again, we can get more output force out of a system than what we input into that system. And we measure this by what we call the mechanical advantage of one of these simple machines. How does the output force compare to how much force we put into that system? So if I have a device that gives me twice the output force compared to what I input, well, that mechanical advantage would be 2. If I have a device that gives me 10 times the output force compared to what I put in, well, that mechanical advantage would be 10 in this case. But even though we can get more output force than we input into the system, when it comes to the work done by that system, the energy being added to the system, work again being force times displacement times the cosine of the angle between the direction of the force and the direction of the displacement, that energy being added to the system, we cannot get more output force than what we input into the system, no matter what kind of simple machine we're using, no matter what the mechanical advantage happens to be. And this is what we're going to demonstrate in this set of experiments. Now, for simplicity, this work equation, again, work is equal to what force is being applied times the displacement, how far is the object that this force is applied to, how far is that object moving, times the cosine of the angle between the direction of the force and the direction of the displacement. In the examples we're going to be looking at, the force and the displacement are always going to be in the same direction, so that angle is going to be 0, and cosine of 0 just gives us the value of 1. So we can kind of drop that cosine of theta term. But let's look at the pulley systems that we're going to be playing around with and some of their general properties. So for this set of pulley experiments, the mass that we're going to be moving is this set of masses that I've put together. This has a mass of 1.275 kilograms. And if we multiply that by the gravitational acceleration on the Earth, little g equals 9.8 meters per second squared, then the force of gravity that is pulling down on this object should be right around 12.5 newtons of force. This is going to be the load that we're trying to overcome in all of these experiments. So I've got a force sensor up here. Let's make sure that this is accurately measuring the force acting on this object. And yeah, within a little bit of rounding, we get right around 12.5 newtons of force pulling down. That is going to be the force that we have to overcome in all of these experiments. Because if I'm just lifting this thing up, I need to apply that full 12.5 newtons of force. We're going to be trying to reduce how much force we need to apply by using pulleys. And these pulleys, they're quite low friction. If I give that a hit, it spins quite nicely. There's 2 pulleys on here. They can spin independent of each other. I can hold one in place and spin the other one. There are going to be some experiments where we do multiple pulley systems. And in the case where we have one of these pulleys, if we have a wheel on an axle with a taut cable around that wheel, if the cable is fairly low mass, we're just going to be using string for this, and the pulley is both low mass and frictionless, then the tension of that string is going to be approximately constant along that entire rope. So the idea is, if I start pulling on this rope, I'm going to be able to support this mass. In this particular case, however hard I pull on the string, that will match the tension force in the string. And again, assuming that this is a low mass, low friction pulley, that tension is going to be approximately constant along the entire rope. So in this case, if I have this sort of a pulley system, I have to apply exactly the same amount of force to that rope that is needed to support this particular mass. So let's set up the pulley system and actually see if that holds true. Okay, so I've got my pulley, I've got the mass that we're lifting, and here's my force sensor. So let's say I'm going to put this on the force sensor. Let me move the force sensor off of this support beam. Okay. So again, if I lift up on this thing, and let me just hold this in place for now. Notice the force that's required to support this is right around that 12 Newton force. Notice there is a little bit of friction on the pulley, so if I let up a little bit, that force goes down a little bit. If I pull down a little bit more, that force goes up a little bit. There is a little bit of friction on the pulley, but we're getting pretty close to that 12.5 newtons of force, where the force of tension in this single pulley system, that force of tension is going to match the force of gravity, the force that is pulling down on this load. Okay. One other thing that we can really quickly verify is, let's say I start with this thing right at the ground, and let's say I want this object to move up, let's say 40 centimeters. Okay. So I want this mass to move up 40 centimeters. Well, that means I have to pull down on this string. So there we're getting the bottom of the mass to 40 centimeters. The bottom of here has also moved by 40 centimeters. So however far I want this object to lift up, I have to move the string down. I have to pull down on this side the same amount of distance. Okay. So when we have a single pulley, just a string wrapped around one pulley supporting a mass, we get the exact same, we require the same amount of force to support this thing or to lift it up. And we also have to pull the same distance that we want this object to move up. So that is with a single pulley, but let's see if we can change this design around to get a mechanical advantage. So for this next design, we're going to have two pulleys involved, and when we look at the forces that are acting on this, let's say I'm looking at the forces just on the end of the string that I'm going to be pulling on. Well, if I'm just pulling on this string, whatever force I pull with, that's going to match the force of tension. And again, since these are fairly low mass, almost frictionless pulleys, that tension is going to be constant along the entire rope. But if we look at the hanging mass, and we look at this as the system that we're interested in, then notice we've got the force of gravity is going to be pulling down on this, and we've got two tension forces that are both going to be pulling upwards. Ropes and strings can only pull on objects. They cannot push on an object. So if there's two strings going up from this mass and the pulley it's connected to, that means there are two tension forces pulling up. So when we are either just supporting the system or having this thing move up at a constant velocity, we're saying it's not accelerating, it's not speeding up or slowing down or anything like that. But if I'm moving it up at a constant velocity, then that force of gravity will be equal to 2 times the force of the tension. Well, we said the force of the tension was the same as the force that I am pulling on it with. So in this case, whatever force I'm pulling on it with, that's going to be able to support twice that amount of force in terms of how much gravitational force, or whatever the force of the load on the other end of the device is. So our mechanical advantage, if our input force is the force of me pulling on one end, and the output force is this force of gravity, in this case, we should get a mechanical advantage of 2. We'll get twice the output force from what we put in. So let's actually put this to the test. So again, if I aim this upwards, the force should be 0 or around 0. Let me make sure I just zero that to get as close as we can when I'm holding this up. So let me hook this side over our system. So again, we've got the string going from where from the point that I'm pulling from, around one pulley, through this bottom pulley, string going up, and that's supporting this this force. So when I give just a little bit of pull to this, when I'm basically just supporting this in place, it looks like our force, again, it depends on if I'm there are some frictional forces involved here, so let me just move this all the way down just so I can push this against the ground and hopefully move it as little as possible. So when I apply those forces, I'm getting a force of around 6.4 newtons. So in this case, the force applied, the force of my pull, is around 6.4 newtons. Okay. And when we compare that to the force of gravity, this mechanical advantage, we have the force of gravity, this output force, divided by the force of the pull, is going to be 12.5 newtons, divided by around 6.4 newtons. And if we combine those together, so 12.5 divided by 6.4, I get 1.95, pretty close to our predicted output mechanical advantage of 1.2. So I got 1.95 for the actual mechanical advantage of this particular system. Okay. So we're getting more output force than we're actually putting into this thing. But we can't get that completely for free. So let's say I'm moving the mass down almost to the bottom, so the string's still taut. Okay? And let's say I want to move this thing up a certain distance. Let's say 15 centimeters is the height that I'm going to try to move this to. Well, if I want to move this up a certain distance, I have to pull twice as far on this object. So that's right around 15 centimeters. Okay, so from where I started, so on here, this is around 39 centimeters for where the bottom screw on this is kind of pointing on there. If I move, so that has moved up exactly 15 centimeters. Now this is at 9 centimeters. I have moved this thing down from 39 to 9. So I've moved this thing's 30 centimeters, and this object has only gone up 15 centimeters. So I'm able to use less force to move this object, but if I'm moving this object, I have to apply that force over a larger distance. When we look at this in terms of the work, the output work would be the force of gravity that is pulling on this thing, or effectively the force of the load pulling up, overcoming that force of gravity, times the distance that it travels. Well, the input force, how much I'm doing, is the force of me pulling times the distance that I have to move. So if I'm moving twice the distance, but only using around half the force, that means those two effects, applying half the force over twice the distance, that will give me the same amount of work output. We can use these simple machines to reduce the force that we have to apply, but we can't cheat energy. We can't cheat work. Now, in this real physical system, notice that our mechanical advantage wasn't exactly 2. This mechanical advantage and the efficiency of this device, there are going to be some losses in efficiency due to things like a little bit of friction on the string. I have to lift other machine parts. I'm not just lifting this mass, I'm also lifting the mass of the pulley. This string, if it had a little bit of stretch to it, I'm trying to keep this string taut because it's more difficult to calculate how much work has to be done during that stretching part. So I'm trying to keep this string taut for this entire thing. But all of those effects are going to slightly reduce this mechanical advantage. And if this mechanical advantage is slightly reduced, then the output work is going to be a little bit less than the input work that we have to do. So the way for these simple machines that we define the efficiency of this machine is by comparing how much output work are we getting compared to how much input work are we getting. And generally we multiply this by 100% to express that efficiency as a percentage. And that efficiency is always going to be less than 100%. It's always going to be a little bit more input work than the output work that we get, even though we're using way less force. Okay. So let's apply the same idea and see if we can look at some other pulley designs to get even more mechanical advantage from these systems. So let's look at our next pulley design. This one, we've actually got 4 pulleys, and we wrap the string around these pulleys in this way and hang the mass from both of these bottom 2 pulleys. So the side of the string that I'm actually pulling on, again, whatever force I pull with, that will match the tension in the strings. But if we look at this system of everything that's going to be moving along with the hanging mass, we've actually got 4 tension forces that are pulling upwards. Which means that the force of gravity is equal to 4 times that tension force. Remember, we also said that the tension force is equal to the force that I'm pulling with. So if the force of the pull is my input force, my output, the amount of force that I'm able to apply to this object, is 4 times greater than that input force. We get our mechanical advantage of 4. But again, there is going to be a drawback. If I want to lift this thing up a certain distance, then I'm going to need to pull 4 times further on this end of the string. Okay. So I know it's going to be hard to see from this camera, but just to kind of verify that this is actually the diagram that we have, on this side, I've got the string going around this pulley. It's the far side of this pulley. That string goes down to the mass through the pulley on the far side of that set of pulleys. That string goes back up, and now it's wrapping around the front pulley on this side. String goes back down, wraps around the other side of that pulley, and goes back up and is fixed in place up there. Okay. So this is the same pulley design, and let's check what the performance is. Again, when I have this thing arranged vertically, the force should be around 0. Let me make sure I 0 that again. And let's move this over so we can actually lift up this mass. Again, the force of the load, if I just hold that under there, the force of the load is 12.5 newtons. And again, it's going to vary a little bit with the frictional forces that are on here, but it looks like we're getting around 3.2 newtons, somewhere around there. So for design number 3, the force applied, again, let me make sure I'm getting a good measurement. So if I'm pulling down on this at a constant rate, the force should go up a little bit. Let's call that force 3.3 newtons if I'm pulling this down at a constant speed. So around 3.3 newtons. Which means that our measured mechanical advantage would be 12.5 newtons for the output force, how much force we are supporting in this case. The input force is 3.3 newtons. And if we calculate that, so 12.5 divided by 3.3, I get 3.8 essentially. So 3.8 for a mechanical advantage. Again, a little bit less than that mechanical advantage of 4, because again, there is a little bit of friction on these pulleys. But if I lift this thing at a constant rate, so again, I'm not accelerating, not doing anything like that, then that force stays around that 3.3. Maybe it would have been a little bit higher, which means we get a little bit of a smaller mechanical advantage. But again, there's things like friction in those cables. Again, not all the cables are going straight up. There's the mass of the pulley itself. But we get pretty close to that mechanical advantage. However, in terms of how far I need to lift this thing, well, let's say I want to lift this thing up 10 centimeters. So starting right from the bottom, I want to lift this thing up 10 centimeters. The bottom of this sensor is at the 48 centimeter mark on this ruler. So if I want this thing to lift up 10 centimeters, I have to move this end down by 40 centimeters. So there, the bottom of the masses is right around 10 centimeters. The bottom of this sensor is right at 8 centimeters. We went from 48 to 8, so that was a 40 centimeter pull distance for a 10 centimeter increase in the height of this load. And again, if we had this, the best possible system, the exact theoretical mechanical advantage, then the amount of force that the amount of work, the amount of energy that we have to add to the system will match the amount of work that is output in lifting this object upwards. I'm using only 1/4 of the force, but I have to apply that force over 4 times the distance. The input work and the output work are going to match. And for this actual system, for the actual measurements that we made, I'll throw up a calculation of what is the efficiency of this actual pulley setup. So let's play around with some other designs as well. For design number 4, we've got another setup where I take the string, wrap it around the 2 pulleys, a 3rd pulley, and then connect that directly to the mass. And for comparison, again, it's going to be hard to see on this camera, but hopefully it'll be easier to see on this one. We've got that string, it wraps around the outside part of that pulley. That goes down, wraps around the outside part of the back part of this pulley, goes back up, wraps around the front side of that pulley, and then I've just directly connected that string to this pulley. Again, that's directly connected to the mass, so it doesn't wrap around again, it just directly connects to that pulley, which is the same as saying it connects directly to the mass. So in this case, once again, on the side that I'm pulling on, the force of the pull matches the force of tension. And if I look at everything that's directly connected to that mass, we've got 3 tension forces pulling up and gravity pulling down. So the force of gravity is equal to 3 times the tension force. The tension force is equal to the force of the pull. So in this case, the theoretical mechanical advantage should be 3. We're getting 3 times the output force that we're putting into this system. But again, the drawback is if I want to lift this thing up, for every centimeter that I'm lifting this thing up, I have to remove basically a centimeter from each of these strings, so I have to pull this thing 3 times further. Let's see how that actually compares with the real performance of this. Again, when this thing is pointing up, we should get around 0 newtons. Looks like it's jumping around 0 newtons, so that's okay. And let's say I'm pulling down this thing, and I'm just going to hold that in place at the bottom here. So it looks like around 4.4. So this is design 4. The applied force is around 4.4 newtons. And when we measure that mechanical advantage, that's going to be the 12.5 newtons from the load divided by 4.4 newtons for the force applied. So 12.5 divided by 4.4, I get 2.84 for the actual measured mechanical advantage of this system. 2.84. Again, not far off from the 3 that we were expecting. And again, we always expect a little bit of loss due to friction, other forces like that. So let's say I want this thing to lift up 10 centimeters. This is actually pretty good because this is right around the 30 centimeter mark, and I want this thing to lift up 10 centimeters. So when I pull this down, in order to get the bottom of this mass going to the 10 centimeter mark, I have to pull this basically back down to 0. We started at 30, we end at 0. So yeah, we need to apply that force for 3 times the distance. Again, the work done, the energy added to the system is equal to the force times the distance. If I'm using 1/3 the force, I'm going to have to apply that force over 3 times the distance to get that same amount of output work done. We can cheat forces, but we can't cheat energy added to the system. We can't get more output energy than we put in. Well, let's look at another example. So in our previous designs, we've seen a bunch of cases where we get a mechanical advantage. We get more output force than we input into the system. But let's have a look at this particular design. So I've got a pulley, and in this case, I've got a mass attached just to the string, and I'm pulling down, I'm applying a force to the pulley itself. So if we look at the forces that are acting on this thing, for the hanging mass, we've got the force of gravity pulling down and the force of tension pulling up. So again, if this thing is either just being supported, not moving at all, or moving at a constant velocity, those two forces will balance each other. On the other hand, if I look at the pulley that I'm actually applying a force to, I'm pulling down on that pulley and there's two tension forces pulling up on it. So if we put this together, we're saying the force of gravity is just equal to the force of tension from this side of the system. But that force of tension is only half of the force that I'm pulling with. So if I'm applying a force on this pulley, I'm only going to get half the output force. So just to kind of show the specific system that I've got here, we've got the string starting at the top here, goes around this pulley. This is where I'm going to be applying forces to the object, goes up around this second pulley, and then down, single connection to that mass. So let's have a look at the actual performance of this thing. So again, we want to make sure that when the force sensor is just pointing straight up, the force should be 0. I was just using the force sensor to kind of hold this in place so everything doesn't just fall apart on me. And let's say I start applying some force to get this thing lifted up. Okay. So if I'm holding that in place, let me move this down so I can just hold this thing in place. Hopefully we don't want it hitting anything else. Maybe I'll just move this to some kind of location in the middle. Okay. So in this case, with this new design, let me get rid of that. This is design number 5. The force applied, in this case, so let me make sure I'm doing this in the case where this would be lifted up, so I'm pulling down a little bit on this. So that force is around 25.2 newtons approximately. Again, it's jumping around a little bit, but around 25.2 newtons. So 25.2 newtons of force. Okay. And in this case, this mechanical advantage, our output force was only 12.5 newtons. Our input force was 25.2 newtons. So in this case, so 12.5 divided by 25.2, that gives me a mechanical advantage of 0.496. Again, pretty close to our predicted mechanical advantage of 1/2. Okay. So why would we ever want to design a system like this? Well, here's the upside of having this sort of a design. Let's see if I want to take this object and I want to move it up 40 centimeters. So I want to move the mass upwards by 40 centimeters. And let's say when I've just got it barely off the ground, the center of this is at the bottom of this sensor is at 27 centimeters. Okay. If I pull down on this side, and again, I want to get the bottom of this right up to the 40 centimeter mark, so right around there. And the bottom of this is right at 7 centimeters. To make this object go up 40 centimeters, I only had to pull down on this side by 20 centimeters. So this is kind of a mechanical disadvantage, but the upshot to it is that if I want this load to move up a distance d, I only have to pull it for half of that distance. In terms of the work that's being done in the system, the input work compared to the output work, well, I'm having to apply twice the output force, but I'm only having to apply that force over half the distance. Again, if I want this object to move up by, let's say, 10 centimeters, if I pull down on this by 5 centimeters, well, we get 5 centimeters extra string on this side, 5 centimeters extra string on this side, so a total of 10 centimeters of the string would be removed from this side, moving this thing up that 10 centimeters. Again, the trade-off in this case is we have to apply twice the input force, but we only have to apply that force over a very short distance. And in certain cases, this can actually be more useful. For example, in your arm, a lot of your muscles have this kind of mechanical disadvantage. If you've ever tried holding a mass out with your arm, just straight out, well, your arm is basically acting like a lever in this case, with the fulcrum being your shoulder joint. The distance from your shoulder joint to the center of mass of your arm, or if you're holding some mass further out, that distance is very long, whereas the distance from your shoulder joint to where your shoulder muscle is actually pulling, that distance is very short. And it's going to be at a very, very large mechanical disadvantage. You have to apply much more force in your shoulder than when you're holding that object further out. The upside is that your muscles only have to contract a little bit in order to give you that full range of motion. So again, sometimes this trade-off actually happens to be worth it. Okay. So there's one more design that I want to look at. We've looked at a number of these different kind of pulley systems. Now I want you to try to design one. So think about the designs that we've looked at so far and see if you can think of how would I have to design a system, a pulley system, such that it has a mechanical advantage of 3/2. So I'd strongly recommend pause the video here and see if you can use the previous examples that we've looked at and put them together in such a way that we can get a mechanical advantage, a theoretical mechanical advantage of 3/2. Okay, so hopefully you actually have stopped the video and try to design one of these yourselves. But let's look at the design. We can actually put together the last two designs that we've had to make this mechanical advantage of 3/2. So here's the basic design, and let me kind of show how I've set this up with this actual experiment. So we've got an anchor point up here. So that string goes around this first pulley, and that's the pulley that is actually connected to the force sensor. That's what we're going to be pulling on. Okay. So that string then goes around the far side of this pulley, the far pulley on that side. That string goes down through this pulley. This string comes back up around the front side of this pulley, and then that last string is just connected to that pulley, connected to the mass. So that's the same design that we have here. String goes around the pulley that we're pulling on, that we were applying that force to, around the pulley at the top, around the pulley connected to the mass, back through the pulley at the top, and then connected to the mass at the bottom. Okay. So when we try to analyze this system and the forces that are acting on this system, if we look at this, the hanging mass and everything that's connected to the hanging mass, well, we've got force of gravity pulling down and 3 tension forces that are pulling up. Okay. So the force of gravity is 3 times the force of tension. Again, when we are either holding this thing still or we are moving this thing up at a constant velocity. As long as there's no acceleration, these forces should be balanced. On the other side, where I'm pulling from, well, I'm pulling down on this pulley, and we've got 2 tension forces going up. So the force of my pull is equal to twice the force of tension. And if I compare these with each other and relate the force of gravity to the force that I have to apply, the force of that pull, we find that the force of gravity is 3/2 times the force that I'm pulling with. It's 1.5 times the force of the pull. So if that force of the pull is the input force, then my output force is 1.5 times that input force. The mechanical advantage would be 3/2. So let's actually measure this system out and see if this matches with our experiment. So again, when no force is applied, and this is just not on the hanger, we should get a force of 0. That seems to be properly calibrated. And if I start applying some force, let me move this just to the bottom and I'll hold that in place. Looks like around 8.5 newtons. So again, our mechanical advantage in this case would be 12.5 newtons for the output force, 8.5 newtons for the input force, and that gives me 1.47 for my mechanical advantage. Again, pretty close to the 1.5 that we were expecting from the theoretical model. But again, there's always going to be some losses due to friction, the mass of the pulley itself having to be moved along with this, any flexing in the string. But again, we get a pretty close matchup between these. In terms of how far do I have to pull this? Well, if I'm getting 1.5 times the output force, then if I want to make this thing move up a certain distance d, I'm going to have to make it move up. I'm going to have to pull down on this side 1.5 times the distance. So let's quickly check that. So when this is just on the ground, the bottom of the sensor is at the 25 centimeter mark. And when I start pulling, let's say I want this mass to move up 10 centimeters, then this side is going to have to move down 15 centimeters. So we're right back to 10 centimeters for the bottom of this object. We went from 25 centimeters to 10 centimeters. I need to move this side 15 centimeters in order to make this side go up by 10 centimeters. And again, if I'm getting 1.5 times the output force, but I have to apply that force over 1.5 times the distance, we are getting the same amount of work done, at least in the theoretical case. Again, our efficiency is always going to be a little bit less than 1, again, due to friction, the pulleys, things like that. Now, there are a lot of other kinds of simple machines, and they have these same kind of properties where we can get more output force, but we can't get more output energy, more output work. So for example, lever systems. If I have a lever where I've got a bar with a fulcrum, I've got some load that is close to the fulcrum point, and I'm applying a force far from the fulcrum point, if we're supporting this system, then we have this balance of torques, and you can show, and I'm sure we'll do some of these in future experiments, that the force of the load will be the distance from the fulcrum to where I apply that force divided by the distance from the fulcrum to where the load is applied at, multiplied by that force applied. So this would give us that R applied over R load, the difference, the ratio between these two distances, that will give us our mechanical advantage. But if I want to move this system up a large distance, I have to push down on this side much further. I get more output force, but I have to apply that force over a greater distance, which means the work done will be the same in both cases. For hydraulic systems, systems that use pressure to make a mechanical advantage, well, at the bottom of both of these pistons, let's say this is filled with a fluid, the pressure just underneath these pistons, if they're at approximately the same height, those pressures will be the same. And pressure is force divided by area. So if this system, if this side where I'm applying that force has a very small cross-sectional area, and this side where the load is, that has a very large cross-sectional area, since the pressures are the same, we can rearrange this and find out that if the area underneath that load is much larger than the area of the system where I am applying this force, we're going to get much more output force than we're putting into it. But if I want to move this system up or down, me moving a certain distance on this side, it's not going to displace very much fluid. It's not going to move this side up very far. So I can get more output force, but I have to apply that force over a larger distance. Same thing for inclined planes. You know, if I have an inclined plane, let's assume this is frictionless. Again, we're looking at ideal situations in this. I don't have to apply as much force to get this to move up. That applied force doesn't have to be as strong as the force of gravity. And you can actually show that as long as this angle is not 0 degrees, this is written kind of a different way than it's usually written out. In order for this to work, the angle cannot be 0 degrees, otherwise this equation breaks down. But for any incline, the force applied is going to be significantly less than the force of the load. This will give us, again, a mechanical advantage. But if I want to push this thing up to a certain height, I'm going to have to apply that force over a much larger distance. In all of these cases, and any other kind of case, we can do the same thing with different gear ratios, with other kinds of simple machines. We can get more output force than we put in. We can cheat forces. But in all of these cases, we cannot cheat energy. We cannot get more output work than we put into the system. Conservation of energy still holds. We cannot create free energy. So hopefully these examples were interesting, and you can try this with try making other kinds of pulley systems or other kinds of simple machines. But we'll call that good for today. And as always, if you have questions, throw them into the chat. Always like responding to those. And thank you as always for the view, and have a good rest of your day.